Okay, this is a video just to explain to you the relationship between what we call the traditional method and the p-value method. You may not realize, but I actually did show you both methods. Um, Most of you end up really just using the p method. Some people still reference both actually, which is a little redundant, but it's fine. So here's the reason that one thing is called the traditional method and one is not. Um, Back in the day, we had, so forever ago, what we had was this. We had this table. So you can see that the number of potential z-scores is small. And so what we'd have to do is look at, well, actually, way back in the day, what we had was this. The normal distribution, if you want to know what's the area under the curve from here to here, if this is already standardized so that this is 0 and this is looks like it's almost 1, so maybe 0.7, if I wanted to know this area, I'd have to use the actual function itself. So I'd have to do, this is going to make no sense to you until you've had calculus, and let me tell you that so I'm going from negative infinity to, in this case, 0.7, and what I'm adding up all the time is this. This is the function, well, this function is 1 over root 2 pi e to the negative t squared over 2. That's the height at any given point, so if this was like on an xy, here's your, can't draw a straight line. If these are your axes, then this function is 1 over root 2 pi e to the negative x squared over 2. That's what this height is. Okay, so if you wrote f of x equals 1 over root 2 pi e to the negative x squared over 2, the graph would look like the normal curve. So, to find the area, and if you take calculus you'll discover this, is you integrate from, in this case, negative infinity. You could really do negative 10 and it would get it all, but theoretically, negative infinity up to wherever you're going, and then integrals add, so you're adding them up. So that's how you get this cumulative distribution. If it's not standardized, then you have your mean and your variance running around as well, so then it's 1 over standard deviation times root 2 pi integral negative infinity to whatever this number would be, e to the negative, and now you have x minus mu, t, x is busy, t minus mu squared over to sigma squared dt. Because in our case sigma is 1 and mu is 0, once it's been standardized, that cancels, that's 1, that's 1, that's 0. And that's how you get this. So that's what we had in the beginning. All we had was, this is what the curve looks like, this is the function, so if I integrate over it, I get this added up. So this is the original way people had to determine area under this curve. Then someone nice, because that, once you get to calculus, you'll realize that actually that is not a fun integral to take at all. So they really would have had to use a limiting process at that time. It would have been a beating to do. So every time someone did the integral, they recorded what the value was. That's where this came from. So basically all of these values, negative 3 up to 3.9, somebody had done it. And they recorded what the value was and they made this giant table. So that fairly close to the beginning of the world, we had these tables. And probably not everyone had the tables. It was probably really just serious mathematicians had the tables, but they had them and they could look. And so now they could say, okay, you know what? I really want to know the area to the left of 1.7395, but I'm going to go with 1.740 and call it close enough because that's already in the table and I don't want to do the scary integral. So we had just these. So we did not have any way to calculate exactly p, So if I wanted to know, I forget now what number I said, but let's say that I said I think it was 1.7395. So I want to know this, and then I would look up 1.74, 1.70, 1, 2, 3, 4, and it's 0.9591. So this is approximate now because I rounded the 1.75, the 1.74, so I didn't have to do the crazy integral. If I was wanting to know, so in the case of a hypothesis test, no matter what the hypothesis test, what we're always doing is saying, I'm going to assume the distribution is as it would be if the null hypothesis was true. So the null hypothesis mean is the mean in the middle. The null hypothesis proportion is the one in the middle. Because if the null hypothesis is true, that's what the distribution looks like. In the case of chi-square, we have a different shape distribution. Everything is positive, so we don't have any negatives, so we're always just looking at that right-hand tail. But what we're always wanting to know is, if I had a sample and I got this far off from my expected value here based on the null hypothesis, was that wildly unlikely? If it was really unlikely that under this assumption, I'm making the assumption the null hypothesis is true, if under that assumption my sample is super strange, it makes me doubt the null hypothesis. So the way we measure super strange is by the percentage that's as far away as ours is. So in this case we want this tail. Or maybe we want both, because if we just want to know, is mine crazy weird, then we want both. But if the question is mine crazy weird to the right, then we can just do one tail. And we define crazy weird by the proportion that's over there. So in this case, what's left from here is 0.0409. Typically, 0.05 is our threshold. So because this is less than 0.05, we would say, you know what, my sample's crazy weird. And so rather than believe that I got unlucky and got this crazy weird sample, what I'm going to believe instead is that the assumption was wrong. That really this isn't what's in the middle. Whatever the null hypothesis claimed was in the middle isn't. Something else is, and I'm really not this far off, because how unlucky would I have to be this far off? 0.0409 of the time I'm wrong, because 0.0409 of the time people are that far off and that unlucky. So there's that chance that I'm wrong. But this is also the reason that we never say I accept the null hypothesis, because we're assuming the null hypothesis and it's an innocent until proven guilty kind of situation. So I actually have to be super confident that the null hypothesis is false to reject it. And I could still be wrong. Okay, because like in this case, I would reject the null because there's only a 0.0409 chance that I'm out there, but that means there's a 0.0409 chance that I'm out there and the null hypothesis is true. So there's a 0.0409 chance that I'm wrong and the null hypothesis is true. So we just are saying, I feel it's beyond reasonable doubt at 0.05 or 0.01 or 0.03, and it depends on how sure you need to be. In this case, typically we pick 0.05, but you wouldn't have to. If it was dead important that you be correct, you'd want to pick something smaller. So that's how we would have used the tables, okay? And the other way to use the table, if you wanted to say what about 0.05, is you would say, okay, well, I'm okay with there being up to 0.05 out here. So what is the number here that gives me 0.05 here? So in this case, I looked up my own value. I found this p-value and compared it to 0.05. Remember, the p isn't perfect because I only have the table. The tables were probably smaller originally. So I would look up and see what makes this 0.05. So I would look in here, and I want this to be then 0.95. So 0.95 is between these two. That's where the 1.645 comes from. It's between 1.64 and 1.65 It's not really 1.645. That is not exact, but it's ish, right? So we would say, okay, approximately 1.645 is the threshold that gives me 0.05 over here. And if I wanted 0.05 in both tails, it ends up 1.96 on a z-table. So then I look this up and see, okay, so if it's 1.645 or anything to the right of that, then it's less than 0.05. Because as I go over, my area to the right gets smaller and smaller. If, on the other hand, it's somewhere over here, then it's greater than 0.05. Because 0.05 is here, so if I come over here, I add something to 0.05, so that's more. So this is my threshold after which things are 0.05. So the traditional method would find the value after which you get the 0.05 or the 0.03 or the 0.01, whatever your alpha is. You find the boundary of that, and that is called a critical value, and this is called a critical region. So that's the part where you reject the null, is if you're past the critical value, away from the mean, or in the critical region. So then I would have just had to look at 1.7395 and say it's over here. It's bigger than this value, so this must be less than 0.05. So that's the traditional method, and this is how the z-value and the critical value relate to alpha and p. So the critical value gives you alpha, your z-value gives you p, and if p is less than 0.05, then z is greater than the critical z in absolute value. So it's further away from the mean. If we were down here, it would be less, but bigger in absolute value. Okay, so that's the relationship. So if I were to, what did I say, 1.7395, use a calculator, if I put in 1.7395, and I'm going to leave this 0 and 1 because I already did want it in standard units at that time. I get 0.959027. So this 0.9591 would have been rounded incorrectly. I would have really wanted 0.9590. But again, it would have taken so much time to have calculated that integral. The calculator obviously did it in a snap, but it's not what would have happened before. So when the traditional method was devised, we didn't have a calculator that did this, okay? So that's what the difference is. Now this would have still told me that it was 0.05. It's a very unusual circumstance where it would end up being a different result if you used a table or not. Okay, so hopefully you now understand how T or Z yields P and how alpha yields then the critical region. So if I know this value, then I can estimate this value with a table or calculate it on a calculator. If not, and if I wanted to do just a bunch of them, then if I know the value to the right of which it's less than 0.05, then I can just compare them. It's very quick and very easy. The other thing is, well, up until William Seeley Gossett in 1908, we didn't have t-tables. T-tables are more of a beating on the integral, but the other thing is with the t-table, which most of you are going to need to use, of course the calculator can do this for you also in a snap, but you're going to need to use this most of the time because your sample sizes are less than 200, and I would really advise using a t-table up until at least 200 because it has the degrees of freedom. Because it has the degrees of freedom, if you're using a table for t, so on the z chart you were able to do kind of 2 digits over here and then 1 up there. you can't do that here because one side is being the degrees of freedom, so it's busy. So the top is the only place you can sort of have a value. So instead of giving a t value up here like this gave a z value on the two sides, the t values are actually in here. They're in these boxes. So what you have to determine is the upper tail probability that you want. So if you want 0.05 alpha and it's one-tailed, then you would use this column only, because that's the 0.05 upper tail. If it was the lower tail you needed, you just make this negative. Same, but it's the same after that. So if you had degrees of freedom 16 because you had 17 people in your sample and you wanted 0.05, then it'd be 1.746 for a right hand, negative 1.746 for a left hand. These are again your critical t's. If you wanted a two-tailed test, still with 0.05, then you'd split it. 0.025 would be in the upper, 0.025 would be in the lower. So then if you had the degrees of freedom 16, then you come over here and now it's plus or minus 2.120. So if you were bigger than 2.120 or less than negative 2.120, then you'd be in that rejection region. So you'd reject the null. So remember that t or z being larger in absolute value makes p smaller. And if p is low, the null must go. I think I've covered everything now. If you have any questions, please email me right away and I will get back to you. So it occurred to me as I was about to publish this that we might want to know the kind of actual value for 0.05 to the right. So you can memorize it or not, it's up to you. You can use that 1.645 or 1.64 or 1.65, and usually that won't be a problem. But if you end up with a t value that's between, or a z value that's between 1.64 and 1.65, then you might be curious which side you're on. Again, typically we're going to use the t, and also typically you're going to use a calculator. So, but if you're curious, which I have become, then let's do inverse normal, and we want the area to be 0.95. And it's 1.64485. So we've been using 1.645. You can see most of the time it would not be the case that you'd get a value between 1.64485 and 1.645. But if you did, then you would have made a wrong call. So anyway, that's the real z value that yields the 0.05 in the right-hand tail.